It's a pleasure to kick off this year's JQI seminars with Sarang Gopalakrishnan. Sarang is a condensed matter theorist and an assistant professor at Princeton of electrical and computer engineering. My best synopsis of Sarang is published in my book. He knows what's coming. Sarang specializes in everything that involves many quantum particles, as well as in a blend of snideness, dark humor, and resignation that's oddly endearing. What's more, before I published that, I asked Sarang if it would be okay if I published that, and he said, quote, "That's much nicer than I deserve, I'm sure." Sarang received his PhD from the University of Illinois, Urbana-Champaign, and he was a postdoctoral fellow at Harvard and Caltech. He had a stint on the faculty of the City University of New York before coming to Princeton. Sarang deals with basically everything in non-equilibrium quantum physics, especially thermalization and the lack thereof. And I personally think of him as a theorist who seems able to explain just about everything in quantum many-body physics. So the floor is yours.
Thank you, Nicole. That introduction was much nicer than I deserve, and I guess I was resigned to getting an introduction of that sort. So, well, here we go. Right. So I'm going to talk today about basically taking many photographs of a quantum system and optical lattice, and what we can learn from those photographs. Am I holding this thing close enough to my? No. Okay, fine. Yeah. Let me do that. Yeah, but that's a bit too close. That's be kind of gross. All right. So the thing I'm going to talk about is based on this discussion I had, this many years long discussion I've been having with Emmanuel Bloch ever since, I don't know, a long time ago. He and Marcus Greiner and others invented this technology of the quantum gas microscope, which is a way of taking simultaneous snapshots of all the particles in an optical lattice at once. And so this gives you an immense amount of information, right? You take you perform projective measurement of all the atoms in a system. And so a good question, a very natural question, is what can you do with all this information? It's much more information than than a simple human can do anything with, right? And so one approach, of course, is to stick it into a machine learning algorithm and do automated stuff with it. But I'm interested in understanding things, and so a natural question from the point of view of interpretable summary statistics of these snapshots is, what can you get out of them that's not just an expectation value or a simple correlation function? And the most natural thing is this object called full counting statistics, which was worked out for some simple systems many years ago in the context of measuring noise in mesoscopic systems. And so the idea is very simple. So you imagine you take a snapshot. Before you do that, you initialize your system with a fixed number of particles on the left side and a fixed number of particles on the right side. So in this image, for example, there's lots of stuff on the left and nothing on the right. So that's some kind of initial condition, but it's not the only initial condition. But the key point is it's an eigenstate of the particle number on the left and on the right. And then once you create this initial state, you let the dynamics run for some time. And after the dynamics is run, you perform the snapshot and you count the number of particles on the left and the right. And therefore, because you knew what these were initially and you knew what they were in the final state, you can figure out how many particles moved from left to the right in the course of the experiment. Right, and this is a number that's it's a quantum system, so it's not an eigenstate of particle number at the end, and so there's some distribution of the number of particles that moved, and so you collect this histogram by doing this experiment many times, and so the mean value of this distribution contains some information about if you imagine starting the system close to equilibrium, so there's slightly more particles on the left than on the right, you can sort of see the mean number of particles moving across the barrier is a measure of the transport coefficient. So it's like telling you the rate at which stuff is moving from left to right. I see there's a question in the chat. Can someone? Okay, cool. Well, I say hello. How are you doing? Yeah.
Just, you say that the change is due to particles moving. How are you ruling out the change is due to particles on the other side just changing state?
Oh, let's, for example, say that we're just counting the total number of particles. But yeah, in general, you're right. If you didn't have a conservation law, there'd be two things going on. But if you do have a conservation law that applies, then the only thing that can happen, the only reason why the particle number on the right can change is the particles move from left to right? But yeah, so in general, this is going to be an interesting quantity, a meaningful quantity when you talk about a conserved charge in the system. Okay, so yeah.
I have a question.
Yeah.
So you have left and right states, and we see this initial kind of configuration.
Yeah.
But each one has like a width to it. So like, what's the difference between in the top image? You know, one of the particles. I guess each pixel is like a particle.
Yeah.
So what's the difference between two different pixels in an initial left or right state?
Sorry, can you repeat the question? I don't really understand.
So you have two states. Why aren't they all on one pixel? Why do you have a spread? Like, how do you know, you have like kind of like a spatially represented image here.
Yeah.
What's the difference between, you know, you have them, they're all say in the right.
Yeah.
What's the difference between two particles in a right state in that initial?
So the picture here, okay, so here you have spins up and down, and so you're imaging them separately. So you're imaging the up particles, the down particles separately. And so each filled pixel on the top image is an up particle, and each filled pixel downstairs is a down particle.
Right, but so it's like you have a block, it kind of has like a spatial, you know, a whole patch.
Yeah, that's
So
this
how
the
do you
initial
choose
state I
which
happened to
one
create.
goes where in this image?
So the image is just picturing where the particles were. So you're asking, how do I initialize the system that way?
Is this actually like a real space image?
Yeah, correct.
Okay.
Yeah, so I guess was that your question?
So it's both real space and they're all in the.
Yeah, so each pixel is a position. There's a position in the optical lattice. An up particle might be that position, a down particle might be that position. And if the pixel lights up in, say, the top image, that means if a pixel lights up here, that means that at that site there is an up particle. Okay. Okay, great. Someone also, I think, chatted his name into the. Okay.
Make the announcement that if people on Zoom have a question, they can unmute themselves and ask, but please don't use the chat because we aren't watching.
Yeah, guys, if you're in Zoom, do not use the chat. I'm going to ignore you. I might ignore you anyway, but especially if you type things into the chat. Yeah, go ahead.
So two quick questions. So one is, so are you assuming both spin and charge number are conserved?
Yes, I'm going to talk about. So spin is a bit of a distraction. Like in this experiment, we did use spin imaging because that was the model we're studying. But in general, you can talk about this question whenever you have whenever you have a charge of any kind that commutes with the Hamiltonian. So you can do energy, charge, spin, whatever. If spin's not conserved, then this is not a very useful quantity because I guess we had a previous question about this. You know, if it can just fluctuate in its own, then it's not going to probe transport.
Well, the reason I ask is,
Yeah.
you have multiple conserved quantities, sorry.
Yeah.
Then it's a different scenario from having one conserved quantity. So,
Well, it's the solution. The solution is different, but the problem is the same, right? So this is right now. I haven't told you any physics. I've just introduced an observable, and I've told you that I'm going to study it. What I'm going to find is a question for the rest of the talk.
and the initial state is supposed to be thermal, or
No, the initial state. Okay, this is very important. The initial state is an eigenstate of the left charge and the right charge. Okay,
which is the same?
it doesn't matter.
It'll be universal.
Well, I mean, the answer is gonna matter, but the observable is defined. Right now, I'm just telling you what I'm going to talk about. Okay, I'm not saying anything about it yet. But right now, I have a system. It's initialized in an eigenstate of the charge in the left half, charge in the right half, and I'm going to run some dynamics and I'm going to count. Okay, and what I'm going to find when I count is the topic of the talk. There's a question back there.
It's a binary variable, why are there different colors?
Because the experiment's kind of crappy.
Maybe
I don't know. No, it's fine. No, it's cool. Like I'm enjoying this. So it's yeah. Please do keep interrupting. Like the less far I go into talk, the more I know what I'm talking about. So okay. So anyway, so the point is that if you imagine these things being if you imagine left and the right charge being very close to each other, this is plausibly a way to do a linear response experiment, because just like saying, what's the rate at which particles are diffusing from left to right, so measuring like diffusion constant or something. But in general, the higher moments of histogram contain information that goes beyond linear response. The question is this information interesting? Like, can you learn something about the dynamics from it? Okay, and so that's so I mean I've sort of already I guess covered some of this, but yeah, so I've introduced an observable, and I'm going to talk about, like, first of all, why this observable might be something you want to compute, and in principle, and then I'm going to give you some examples of what it says about many body systems and a couple of cases of interest. First, I'm going to talk about the generic behavior, and I'm going to talk about a case where you see something really anomalous. And I was gonna get the strange case of Heisenberg model, but given how we're doing on time, like, I don't expect that I'll actually do so. Okay, right. So the motivation for this work, and like really any work on quantum dynamics and cold atoms and systems like that, is that you want to study this unusual regime of unusual from a traditional condensed matter perspective regime of many body systems, where they're both isolated and hot. And so in traditional many body physics, like if you're talking about a slab of metal or something, these conditions are not really possible to satisfy at once, because an isolated system means you want the phonons to be inert, and high entropy density means you want to be at high temperature. So in a normal electronic material, this regime is inaccessible, which is why Phil Anderson didn't figure out in the 1960s, and which is why we still have employment in condensed matter physics. But nowadays, there are many systems in which it's quite natural to realize both these things at once. In cold atoms in particular, the isolation is easy. The thing that's hard is getting them actually cold relative to their naive energy scales. Okay, so that's this regime that we're going to think about, and this regime has the feature of breaking the standard paradigms by which we study many body physics. And those paradigms really involve the idea of elementary excitations that are present in some dilute limit. And so you can think about that either in the Andersonian way, as like, oh yeah, I have some ground state, the ground state's non-trivial, but then my state I'm actually probing consists of ground state with a sprinkling of elementary excitations. Or you can think about it from this Matt Hastings perspective, which is more natural for numerics with tensor networks, things like that. Where you say, oh yeah, Hilbert space is gigantic, but you only really care about you only care about low entanglement states. And so if you're hot, then it turns out that first of all, the excitations are dense and there's soup of them. And second, the entanglement is high. It goes as a volume law of the region you're considering. And so none of these microscopic methods really work, at least in a naive sense. And so, does that mean this problem is really hard and we can't say anything about it? Well, no, if you went to Anderson and told him this, then he'd say you're being ridiculous. This is just the wrong way of thinking about it. If you wanted to study water flowing through a pipe, you wouldn't start with chemistry, you would do fluid dynamics, right? And so correct way to study things at high density when they're strongly interacting is to use the complexity of the problem to help you. So high temperature dynamics is chaotic, and what chaos allows you to do is it allows you to say that a state is basically random. It's like about as it's got some energy density and some particle density, but conditioned those constraints, it just goes into the max entropy state that it's allowed to go to. And that's this idea that chaos basically randomizes the state, and think about the state of a chaotic system as random is what's called thermalization. And hydrodynamics basically just consists of applying thermalization locally. So you say you have a tube, you chop the tube up into little bits. You say each little region of the tube is defined by its locally in some thermal state with some density and some temperature, and then you say, okay, how do these density and temperature profiles evolve in time? And so that's a paradigm. If you're actually talking about a fluid in 2 dimensions and 3 dimensions, this is a very interesting math problem. But if you're thinking about a particle in a lattice in 1 dimension where momentum is not conserved, then this is a really simple, the hydrodynamics of these systems is really simple. Every conserved quantity just undergoes diffusion. So that's the idea. And so the whole problem of understanding microscopically what high temperature dynamics does is just a question of computing the temperature dependent diffusion constant. And so this is an interesting numerical problem, but maybe theoretically we don't care so much about what the diffusion constant is. But there's a question of, does it work? Is diffusion in fact all that's going on? And there's sort of 2 reasons to doubt this. And the first is that we've had about 20-25 years of cold atom experiments, and we've seen a number of different situations, both predicted and sort of discovered serendipitously, in which this program of hydrodynamics never really gets off the ground because the system doesn't thermalize. And so in these systems that don't thermalize, you have a new kind of problem, which is that you have lots of long-lived excitations. They're present at finite density, they interact with each other. And so these 2 ideas, so there's a paradigm of hydrodynamics, and that works when you have a small number of conserved quantities that you can write down diffusion equations for. Then there's another paradigm of working with elementary excitations that might be long-lived, but they're dilute. And so when the excitations are when there's lots of long-lived modes, then you sort of, both these paradigms break and you have to do something else. And so I'll talk a little bit about what that something else is downstream in this talk. So that's one reason to worry about hydrodynamics. A different reason to worry about hydrodynamics is that hydrodynamics is really a theory about something like a density profile in a classical system, right? So it's a theory about the expectation values of simple observables. And so when you ask, does the system thermalize? The full quantum state of a system never really does thermalize, right? Because you start the system out in a pure state, it ends up in a pure state. A pure state is not a thermal density matrix. What thermalization is it's an ansatz about simple local observables. So it says that if you look at the problem doing some kind of simple experiment, then you cannot distinguish this guy from that guy. Right, but what is simple, what's local, how non-local do you have to be in order to see that the system isn't thermalizing? And so we have at least one data point on this, which is the full output distribution. If you were to measure a system on an arbitrary basis doing a rank 1 projector, and look at the distribution over those outcomes, that histogram does contain some information about whether the system is in a pure state or a mixed state, right? That's the whole basis of say, the Google quantum supremacy experiment, every other random circuit sampling experiment like it. So, at some point when you go from simple objects to complicated objects, this paradigm has to break down. And so, traditionally they said, okay, who cares? We can't look at a complicated object, but we can. And so the question is, how complicated do you have to get in order for the in order to see these features of the system that doesn't thermalize? Okay, so that's the motivation, and then so we're gonna sort of a few different ways of trying to study it. The first is what Emmanuel Bloch does, which is to look at a cold atomic system under the microscope. So the big advantage of this approach is the coherence times are great, the system sizes are great. The sort of limitation of the approach is that collecting samples is hard. It's kind of slow. You can get a few thousand maybe, but it's hard to get like large numbers of samples. Second approach is a digital quantum simulator, like a superconducting qubit system. I'm going to talk about that later if I have time. The good news is that it's easy to collect tons of samples, but the downside is the coherence times and system sizes accessible are not great. You can get up to like 50 odd qubits. And I should say that because the coherence times are not great, and you have to mitigate the sort of not great coherence times using post-selection, the sampling advantage is not really that substantial, because like all your 10 to the 6 samples are eaten up by post-selection. You kind of have the same number of samples nowadays as in a cold atom system. But in principle, that could improve. And finally, these are both kind of competitive right now. We're just naive simulation and classical computers. Classical computers like very programmable, so that's great. They have this exponential scaling of complexity with system size at time. That's not so great. So nowadays we're getting to the regime where the experiments can tell us things we can't simulate. Another upside of classical computers is you can just like pull off the probabilities at once. You don't have to sample at all. Just like pull out the probabilities from the wave function. So yeah, that's sort of those are the 3 things I'm going to talk about. I mean, those are 3 platforms in which you can think about full counting statistics. What I'd really like to do is I'd really like to talk about the theory of full counting statistics in certain types of systems, and what we can what it tells us about many body physics if you can go and measure it somehow. But this is how you go and measure it if you wanted to. Okay. So I guess I had a bunch of questions already, but things have quieted down considerably. So any questions now before I keep going? All right, let me keep going. I hope it's not because I've lost everyone, because I didn't mean to do that. Okay, so let me talk about what I expect full counting statistics to do in the most generic chaotic context. So So what I want to do right now is I want to talk about a quantum system that's I want to think about quantum systems that are kind of generic. So they're boring. There's no particular structure to them except locality. And I want to understand what this observable does in the context of these systems. And so in order to understand what it does, I need to set expectations. And so the simple-minded expectation is that the dynamics of a chaotic quantum system on a lattice is governed in some sense by the diffusion equation. So let me take a paradigmatic classical system that undergoes diffusion and understand the distributions there. And let me use that as a basis for, I don't know, setting expectations for the quantum system, and then I can see if the quantum system actually does what it's supposed to do. So this classical system that I'm going to work with is the exclusion process. The exclusion process is it's a fancy name, but it's a really boring classical process. What it consists of is a bunch of particles in a line. They're on a lattice. Each side can either have 0 or 1 particles on it. The particles diffuse around, except that if there's already a particle in a site, then a new particle can't diffuse to it because the site is blocked. So that's the symmetric exclusion process. And if you imagine measuring the full counting statistics, well, what's counting statistics over? Well, there's sort of two potential sources of randomness. The first is the initial condition could have positional randomness in it. It's an eigenstate, the left particle number, the right particle number, but the distribution of particles could be random. But the other source of randomness, of stochasticity, a thing that gives you a distribution function, is the fact that dynamics is noisy. So at each time a particle flips a coin and decides whether it's going to try and hop or not. Okay, so you can compute the histogram of these of the particle number on the right over both of these variables, over both these sources of randomness. And the sort of remarkable thing is that you can solve this model exactly, and it gives you the same distribution as you would get if you just solved this kind of nasty stochastic equation directly. And the fact that this feature that the full distribution function in the classical problem is in some sense universal, because it doesn't care about the details of the exclusion process. It just cares about these coarse grained quantities. Gives you some hope that that this might form a basis for understanding the statistics in more general contexts. Okay, so classically you have noise, you have randomness in the initial state. What does this have to do with a quantum system? And so the basic idea is something like this, or the way you would justify why a quantum system might have the same statistics as a classical stochastic process goes something like this. You have this time evolution that generates a highly entangled quantum state. But you say you invoke thermalization to say that this highly entangled quantum state is kind of like a classical thermal ensemble. Okay, and now you have a classical thermal ensemble that's a source of randomness. And now what you say is that the dynamics of the classical system is chaotic. So what that means is that even though sort of coarse-grained hydrodynamic modes evolve according to more or less slow, everything else, the generic degrees of freedom in a classical chaotic system sort of fluctuate rapidly, and so they act as effective noise on the slow modes. And so with this two-step process, you might say, okay, even a quantum system might be described by just noisy evolution of hydrodynamic modes, which is sort of what this equation gives you, and so you might expect that the counting statistics might be the same. Okay, so but this is in some sense a highly non-trivial set of assumptions, and so it's something you're going to have to test, either by doing exact calculations or by doing experiments. So there's one context in which we can do exact calculations. Well, I mean, by we, I'm being kind of generous. My postdoc, Ewan McCulloch, can do calculations. So that's the context of random circuits. Now, I assume you've heard talks about random circuits in the seminar series in the past. I don't have time to go into the details of how you do these calculations, but the basic idea is that for random circuits, you can actually compute many things in a controlled way using the mapping between random circuits and stat mech problems. I just have time to quote the bottom line here, which is that we can do this calculation of random circuits. We can compute the full counting statistics of a typical instance of a typical random circuit, and this full counting statistics itself can be shown to have the same distribution as you would get in the classical stochastic process. Yeah.
I should ask this, but your diffusion equation has a noise.
Yes, that's very important. Yeah.
Yeah. So the full counting statistics are sensitive to that noise term.
Yeah. In fact, that's all they're sensitive to, right? Because if you didn't have the noise, you wouldn't have a distribution at all.
You would still have distribution over initial states.
That is true, but if you had large scale density fluctuations that were random, you would. But I'm going to talk about situations in which the initial state is kind of like it's uniform on one side and uniform on the other. And so the noise in that context, the noise is sort of the only thing that's like creating a distribution for you. Right. And so right, so at least in theory, this idea should work. And so let's see if it works outside the context of noisy quantum circuits. Can it work for a chaotic Hamiltonian? And so there, of course, you can't really do anything but run experiment. And so that's what Monica Eidelsberger and Emmanuel Bloch did. And so the chaotic system we considered there was hardcore bosons on a two-leg ladder. So so the idea is that I don't know, like, okay, so this is your system. There are two, so it's really a two-dimensional system, but there's sort of big barriers separating each two-leg ladder from every other two-leg ladder. So it's an ensemble of decoupled two-leg systems. And so within each two-leg system, you have a hopping along the leg, and you have a hopping sort of between the legs down a rung of ladder. And so we start out with this initial condition. Notice there's no randomness at all in the initial condition. That's important. So the only randomness is sort of self-generated by quantum fluctuations. So you start out with this initial condition. It's pretty obviously an eigenstate of the left and right number. And then you let the system go. And you ask, well, you know, what does it do? Does it, you collect these histograms. And right now, unfortunately, the noise is such that we can't really do more than like understand the variance of these distributions. That's already telling you something interesting because, again, like conventional hydrodynamics is just a theory of expectation values. It doesn't tell you about any non-trivial moments. Right. So what we do is we look at yeah.
Initial state, is it just a Mach state?
It's a density wave, right? So it's got
Sorry? Oh, it's
Yeah.
every other side.
yeah, it's every other side. Thank you.
Okay.
Yeah, I guess that's not really visible, is it? Sorry. Yeah, no. Is that what's happening? Like, okay, fine. Was this the only place where it was a problem, or was it not? Because I have no idea. I use my iPad. Okay, sorry.
Most of it's black and white, so it's.
Yeah, so I guess what's the
Because it was bad on the slide.
all right. Well, I mean, it's
I can make it really dark in here.
so does anyone want to tell me how to like change my brightness settings, because I don't know how to use this object? Is it that thing? Oh, right, cool. Okay, cool. Is that
Nothing.
yeah, okay. Well, it's worth a try. Okay, so that's the question we're asking. We're trying to understand, like, starting from this like every other side state that's like very uniform and such, going to go to sort of random density distribution at late times under this chaotic dynamics. How's that going to work? Yeah, go ahead.
I think in the previous slide, you mentioned that like these are quantum fluctuations, not initialization.
Right.
Initialization.
Correct.
So, how can you tell? Like, is there,
Well, so I mean,
how do you distinguish between the two?
so the way you distinguish between the two is you create the state, and then you can measure it at time t equals 0, right? And that gives you some distribution. And you're right, that distribution, I would like it to be a delta function. It's not really a delta function. It has like, I don't know, like 1% variance or something, but over time that variance builds up. So what we're studying is the build up this variance over time. And so, so I guess that answers your question, right?
As long as
Yeah.
it's like
Yeah.
kind of
Yeah.
delta function, or
It's narrow initially and then it broadens. Yeah. Yeah, right. Precisely. Yeah. David.
So you gave this example of the symmetric exclusion process where things ended up being determined entirely by the stochastic diffusion.
Yeah.
To what extent is that generic even in classical systems?
It is generic, and so the okay, so there's a question of how you test these things in classical systems. So what we believe is that at least in a wide range of classical stochastic processes, this equation is all there is, right? It's a diffusion equation with multiplicative noise. And the multiplicative noise tells you that, if your density fluctuates, then your conductivity and your diffusion are going to fluctuate with it. And that's sort of all there is at the coarse-grained level. And so that's been checked in a number of classical stochastic processes. It's also, I believe, been checked to some extent in chaotic classical automata of various types. But yeah, even in classical systems, the claim of this universal is sort of a non-trivial claim that you can't really, you can't analytically treat in general. But classical numerics is pretty good. In quantum systems, you don't even really have that, so you kind of have to do something else, and in this instance, something else is experiment. Okay, so right, that's experiment.
What's the philosophy right now? So you have a hydrodynamic equation,
Yeah.
and then you have some experiment,
Yeah.
and you want to see to what extent this formula satisfies this.
Yeah, you want to.
Other possibilities.
The other possibility is that it just doesn't work, right? I mean, and there'll be aspects that we'll see where there'll be cases where this doesn't work.
And this is a class, so this is just observable security right now.
This is a particular observable, and it's the reason I'm choosing this observable is it's not a low weight observable. I'm performing a rank 1 measurement, looking at statistics, a rank 1 measurement.
Hydrodynamics is always for density and current, and observable is not for like larger.
Yeah, that's in some sense what we're checking, right? So hydrodynamics can be sort of naively used. I mean, I can naively use this ansatz that like everything is just the exclusion process, and I can see if it works. It makes some very non-trivial predictions, and so I can see if those predictions are satisfied or if they're violated. And so that's what I'm trying to do. Okay, I'm going to give you some examples later where I have a reason to expect them to be violated, and they are in fact violated. But right now we're just like seeing, in a system that's as boring as possible, do things work out? Okay, that's what we're doing right now. So I mean, it's great because I'm gonna like I think be stuck at the boring part of the talk, which is fine. It's like, but yeah, it's okay, but like the last. Yeah, sorry.
Okay.
Yeah.
What are you looking at the fluctuations of? Is this the anti-ferromagnetic order parameter?
No, it's this thing that I was talking about, right? So you take a system, you sort of initialize, you have a barrier in between the left and the right, or you have some initial state that's like an eigenstate of some charge on the left and on the right, and then you lower the barrier and let the dynamics go. And then you have some distribution of particle numbers in left and right.
So that picture made sense, but how does which left and right in this experiment?
So left is it's the same thing. It's like I cut the system somewhere in my mind, and I count. So the left is everything to the left of like this point, and the right is everything to the right of that point. And the initial state is some eigenstate of the charge in the left and the right. And in fact, the same charge. Which is sort of it's again the simplest case you can come up with, and you want to see on average nothing happens, right? And that's sort of why we chose the initial condition. On average, nothing happens here. On average, the system like very quickly relaxes to a uniform density profile. But the key thing is that even when the average is completely like uninteresting and relaxes fast, the fluctuations build up over time. And what we're doing is we're looking at the build up these fluctuations and the dynamics are there. Okay, right. Okay, and so you go look at it and experiment, and so we only really look at the first couple of moments, but even the second moment tells you something kind of interesting because this object, if you think about it, the 2-point correlator of the instantaneous 2-point correlator of density is a totally different object mathematically from what you would normally call the 2-point correlator in a condensed matter setting, which is it's sort of an unequal time correlation function. That's what you normally measure. The second thing is what you normally measure when you measure that if you wanted to study transport. But fluctuating hydrodynamics makes a precise quantitative connection between these two correlation functions, and so you can check that experimentally, and so the surprising or the interesting thing is not only does the overall picture work, you know, in the fluctuations build up in a diffusive way, but the diffusion constant of these of the build up these fluctuations is precisely the same up to, you know, quite small error bars as the predicted equilibrium diffusion constant. So that's sort of a relation between these two mathematically distinct but physically similar quantities. And so that's both kind of conceptually nice because it tells you that fluctuations really do build up in a quantum system in a hydrodynamic way. But it also gives you a rather nice way of measuring diffusion constants, because if you wanted to measure diffusion constant in an experiment, what you normally do is you take the system out of equilibrium, but you create sort of large scale density imbalances. But here all you're doing is you're measuring fluctuations in a system that's sort of homogeneous in large scales. Yeah. The numerics, there's a bunch of different things, but there's both TBD and Dowie. You know Dowie? Yeah, so Dowie extrapolated to like zero noise by the guys that do that stuff. Yeah.
No,
I was just gonna say this was, I think this was in the Dowie paper, and I just like it's that same one.
Yeah, so it's actually kind of amusing because I didn't realize this. So it's like, you know, no one's ever looked at this model before, but then at some point, like Tibor Rakowski pointed out to me, yeah, you know, we have a number for this. Yeah. Okay.
So sorry, so are you saying that you can't measure the structure? Can you measure the structure factor in an experiment?
No, actually, so you can measure the structure factor in principle by taking the system out of equilibrium and measuring a response function. But it's very difficult in this context to do a linear response experiment, because in order to get enough contrast, you need to take the system pretty far out of equilibrium.
So I thought you made a comment about you can check the correspondence between these two.
Yeah, so the way you do that is basically that you measure this guy in experiment, you measure this guy in numerics, and you find that they match.
Okay.
Quantitatively.
Numerics, you can measure the first guy too, right?
You can measure the first guy in numerics, but it's a lot harder because that involves doing a far from equilibrium problem. Whereas what you do in the second numerical calculation is you just do the Heisenberg evolution of an operator. And then you just sandwich it with the original operator. So that's a much measuring an infinite temperature.
For an infinite temperature. So EQM would be the infinite temperature.
Yeah, equilibrium here. You know, because this guy, this initial state that I had, it's like, you know, it's obviously a far from equilibrium state, but it's at half filling, and its energy density is the infinite temperature and energy density in this model.
That was the ground state of the Hamiltonian.
Oh God, no, absolutely not. No, this is not the ground state. The ground state is like a superfluid or something. But the state is at this filling. This is not the ground state.
Even before you remove the barrier, it's still not the ground.
Yeah, it's absolutely not the ground state. The ground state, this model, this is at a fractional filling, and the ground state is Latinger liquid.
Okay.
Yeah, so that's very important. Yes, this state is at high temperature. It's at high temperature, which is why you expect it to behave hydrodynamically, and it does behave hydrodynamically.
Okay, but before you remove the barrier and let the thing go, it seems then why would that state even be state?
Oh, because you don't create it. Yeah, so I don't let it equilibrate. What I do is I start out the totally different Hamiltonian, where some sites have like very deep wells and some sites have nothing at all. I create this ground state by loading into ground state of that Hamiltonian, and then I turn off that Hamiltonian, and then I turn off the barrier it was.
This is the ground state of the initial Hamiltonian.
Yeah, which I'm not telling you anything about. It's not the ground state of the Hamiltonian that governs the time evolution. But yeah, in principle, I created it as the ground state of some Hamiltonian. In principle, you know, I could also have created it by just like putting particles down somewhere and like letting it go very fast if I had that kind of like temporary resolution. All right. So that's observation one. And so even here, we find something interesting in both the experiment and the numerics. So you let the system go for a very long time, and you ask about how these fluctuations saturate, the value at which they saturate. And so what you find is they saturate at a number that's substantially smaller than the thermal expectation value for this temperature, which is infinite temperature. So what you expect is that you're going to end up with 50% chance of each site being occupied or empty. And that's what you expect the system to alter at very late times. But what you find is the fluctuations never really quite build up at that scale, both experiment and numerics. So at late times, the half system fluctuations seem to saturate to a subthermal value that doesn't seem to be getting better with system size. And so this is an interesting observed violation of thermalization that we don't understand, but it seems kind of robust. Yeah, Mohammed.
Is there a possibility to benchmark this with just the classical walls that have been on one side of the box?
Yeah, so in a classical system, see, the thing is, if you did exactly this experiment in a classical system, you would not get a distribution at all, because the initial state is deterministic, the dynamics is deterministic. So you would just get you get some particular configuration, right? So in order to make this experiment work classically, you'd have to have some external source of noise.
Yeah.
Once you add noise, it does thermalize to infinite temperature, yeah.
And in the experiment, they have.
No, they don't. Not in these time scales, right? Because I mean,
We don't know many about the echo experiments. So how at time t0,
Yeah.
I was with you, but
Yeah.
then when they do run the experiment, how you're really sure that you're not.
So we haven't done a precise measurement of coherence in this experiment, but we're talking about optical lattice experiments in which various like echo type things have been done on these timescales. So we expect that whatever decoherence processes are going on are not yet operative. So we expect them to be operative on timescales, based on other experiments in the same setup that are like around. They're around like 50 or so in these units. I'm looking at times that are like 10 or 20. So if you did you did a classical experiment with the same noise, the noise just wouldn't build up on these time scales. Okay.
So just as a sanity
Yeah,
check,
yeah.
you let it go for equals 50, so you expect the thing to be here? Do you see the expected classical type thing?
We just don't run the experiment that long, because on timescales that are that long, you also have to deal with amplitude damping noise, which is basically like particles leaking out of the system. If you never actually get to the infinite temperature classical state, the noise is not right for that. But yeah, so this plateau is well before that happens. In any case, that wouldn't give rise to plateau. But yeah.
I'm just out to diagnose some of the weirdness, but you can't see that.
Yeah, you can't see that, but like, yeah, it could be some other weirdness going on. Yeah.
You missed something. What's the y-axis in the first plot?
Sorry, I didn't present that, did I? The good thing about an iPad is I can just write it in. There you go.
They're variance in the total density.
And on the right-hand side of the system. Yeah. Okay. Fine. So that's the case where it mostly works. I guess I have like something like 5 minutes left. 10. Okay. Fine. So let me just like very quickly zip through like some part 2 of my talk, and then I will stop. Okay. So that was a chaotic case, and I'm going to say a couple of like quick things about the integrable case. And so integrability is one of these things that frightens people, but it's really very simple. Like if you've studied trolleys in a frictionless track, you basically understand it. So you have trolleys in a frictionless track. They're identical. 2 particles come in with 2 velocities. The 2 unknowns, the 2 final velocities, the 2 constraints, conservation of energy, conservation of momentum, and those completely fix the final answer to be like the particles just exchange their velocities. So that's all that happens. And in general, like if you had, say, a 3-body collision, this feature would break. But in many systems, 3-body collisions have this property called integrability. And so when that's true, then what you see is that you just have collisions like this. And these collisions preserve the set of total velocities. They just permute velocities amongst the particles. They don't change the velocity distribution. Right, and so you want to study the dynamics of an integrable system. What you do is you follow, you define these things called quasi-particles, and they're objects of particular velocity. So they live in a trolley. When 2 trolleys collide, they jump from one trolley to the next, because the trolleys exchange their velocities. So these objects, these quasi-particles, move ballistically. And so in terms of these quasi-particles, the dynamics of an integrable system is simple. But in terms of the physical observables, the dynamics is very hard, because the relationship between these trolleys and the physical variables is highly non-trivial. So about 7 or 8 years ago, after many years of struggling with this problem, Ben Douillon and others discovered this framework of generalized hydrodynamics, which computes the dynamics of densities and such in integrable systems. I don't have time to introduce GHD, but the naive version of GHD says that everything in an integrable system, all conserved quantities in an integrable system move ballistically along with the quasi-particles. But what you find when you do numerics on the simplest integrable system, which is the XXZ spin chain, is that you actually have this dynamical phase transition in the transport properties. So depending on this parameter delta, you have a regime where things behave the way you expect them to behave, where all transport is ballistic. But you also have this other regime that's kind of interesting, where spin is transported diffusively, even though the quasi-particles are moving ballistically, and you have ballistic energy transport. And between these two phases, you have an infinite temperature phase transition, which I won't have any time to talk about, where transport, but we understand some things about it, where transport is super diffusive. With this interesting exponent, there's an entire story associated with that, but I don't have time for that. What I want to talk about today is this extreme, yeah.
So this is all for the infinite temperature state?
Yeah, it's actually true for any finite temperature. Yeah, any non-zero temperature, you have this phase transition in transport.
And with the same value of delta, which
yes. Yeah, it was surprising, right? But that value of delta it's not so surprising if you realize there's an SU2 symmetry at that point, which is not there anywhere else. Yeah, it's a Heisenberg point. So it's sort of not surprising that it's special. But it's surprising that there's anything at all at finite temperatures, right? Because at finite temperature, you don't expect phase transitions. But this is a dynamical quantity and not a thermodynamic quantity, so it's okay. Right. Okay, so let me just say, yeah, so in the limit of very large delta, this problem becomes simple again, because basically what you find is that this term is the dominant one, and what this term does, it attaches an energy to every state, depending on the number of domain walls in that state. And so in the infinite delta limit, the number of domain walls is conserved, and so when the number of domain walls is conserved, you can say that this Hamiltonian reduces to a problem where a spin can hop from one side to another if its hopping doesn't change the number of domain walls. And so the spectrum of this model consists of 2 types of objects. It contains objects like this, like let's say 3 upspins and a sea of downspins. So this can't move at all, because first of all, none of the spins can move individually, because that would change the number of domain walls. Second, the domain can't grow or shrink, because that would violate charge conservation. And which is the total number of upspins in this model. And so this object is stuck, but a single flip spin that's a magnon can move around freely, and in fact does move ballistically, because the model is integrable. And the key feature, which I think is all I have time to talk about today, is what happens when these objects collide. So when a magnon collides with a big domain, you can sort of work it out. So magnon comes in. It sort of stops here. It can't do anything, because if it kept moving, it would kill 2 domain walls. So it can't do that. It's either bounce back, or it can sort of transmit through the big domain by flipping its polarity. And in the model, in the integrable model, that's the second thing is what happens. So a magnon that's upspin hits a domain of downspins. It hits a domain of upspins, and it goes through the domain by flipping itself to be a downspin. And so in an infinite temperature state, there are as many up domains as down domains. So magnon is up half the time and down half the time. So that's why it doesn't carry spin ballistically. On the other hand, when the magnon moves through a domain, it causes the domain to undergo Brownian motion because it kicks the domain 2 steps the opposite direction. So over time, this big domain gets hit by magnons coming from the left and the right. And so that gives you Brownian motion, that gives you diffusion. Okay, so the basic bottom line of what I'm going to talk about, I don't really have time to describe it in detail, is if you now consider the full counting statistics of this problem, what you find is that in fact it's really anomalous. Instead of the distributions being Gaussian at late times, what the distributions look like is like half a Gaussian. So it's like the absolute value of a random walk. And that has a couple of interesting implications that are very different from chaotic systems. And I'll just talk about the one most striking one, which is that in this integrable system, both the mean and the variance, both the mean and standard deviation scale as the square root of time, because it's really just one random walker moving around. Whereas if you had a chaotic system, what you would expect is that these have different exponents because over a time t, particles have moved across the distance square root of t, and systems equilibrated over that distance, but the equilibrium fluctuations are the square root of that again. And so the standard deviation should go as t to the 1/4, even though the mean goes as t to the 1/2. And so the big difference between the chaotic case and the integrable case is that in the integrable case, all the diffusion is being done by one giant random walker, whereas the chaotic case, hand-wavily, there's a large number of independent random walkers. And so you have this like striking, even though the mean transport is diffusive in both cases, the moments behave in a totally different way. Okay, so you can check this numerically, and so there's sort of a long story about that. But yeah, so the bottom line is that this is it's a rather simple example of a model where even though on average transport behaves just as it would in a chaotic system for spin, in fact the fluctuations are totally different, and this difference can be seen in experiments doing full counting statistics. Let me stop here because I think this is about as much time as I have, and take questions.
So you made this comment when you were talking about the deviation from the late time and variance from the critical value earlier, where you said the classical system, that you like couldn't define a classical system that was like in the same kind of paradigm. Is that how I understood your?
Yeah, because this is a deterministic initial state, and the dynamics is deterministic. So classically, it doesn't mean anything. Talk about distributions.
Well, I don't know if I agree, because you could start with like the truncated frequency dynamics, right? So you could look at like the phase space associated to your quantum system, and then just like forget all the quantum mechanics. Like that's a classical system that should approximate your quantum one.
But I mean, yeah. So if you put in fluctuations via truncated Wigner, then I would say that's a quantum system, even though you're actually, doing some kind of classical algorithm to simulate it.
Well, it's like classical phase space dynamics.
But with quantum distribution over phase space, yeah.
Right. But okay, so I guess my question was like, do you expect that such a system as that would also show this deviation?
No, I don't.
Okay.
There's absolutely no reason to expect it in that context. We've not actually explicitly done truncated Wigner simulations this model, but yeah, based on like the other classical simulations related models, there's like no reason to expect this persistent deviation there. Yeah.
So if I understand correctly, the experiment that you showed in Munich, did not use full counting statistics. It done it just looking at density at each side, and if this is the case, if I understand correctly,
you gotta.
What can you do with counting statistics?
So this is, so it looks at this. This already is in some sense full counting statistics, right? Because it looks at, I mean, it's only the variance, the full counting statistics. In principle, the higher moments would contain even more information, which we just can't access because our signal to noise is not good enough. But the variance is already a measure of fluctuations, right? Because you're taking instantaneous snapshots and you're asking what's the variance across snapshots. It's not an expectation value. Right, if you're just measuring expectation values, nothing would happen. Like the system would have some very quick order one time relaxation, that would be it. The density would be uniform. So yeah, so this does require like the ability to take snapshots and do statistics across snapshots. It just happens to be a very simple statistical measure that we're talking about. This is site resolved.
So not average over variation, the whole system.
Well, you're not averaging, right? You're counting. Yeah, well, I mean, yes, you can measure correlations between the number of particles to the left and the number of particles to the right, and measure these covariances, and those contain more information about like fluctuations. But the point is, I mean, the question is, what's a simple thing you can get? What is a simple thing you can compute that goes beyond expectation values? And so this is the simplest object you can measure that goes beyond expectation values and measure some aspect of distribution. So in a different experiment, which the
diffusion constant you can actually measure without variance.
Yes, but that's a totally different thing, right? So these are different objects. So there's sort of two things going on here. The first is that you're checking if this mathematical object is consistent with that mathematical object. They're totally different the way they're defined, right? And so the fact that they coincide is a non-trivial test of fluctuating hydrodynamics. The second thing is, it turns out this is a nice way of measuring linear response diffusion constants because if you were to do the experiment measuring expectation values, you'd have to create a pretty far from equilibrium initial condition to get the signal to noise to measure diffusion constant. So this happens to be the most accurate way of measuring diffusion constants. That's sort of a different. That's a side effect.
Then quite a number of questions already, so I guess we have time for just one more.
Yeah.
In the anomalous case, I'm wondering if you see the anomalous full counting statistics in the regime where the spin is subdiffusive, like with equals 4, or do you see diffusion and distinct?
Yeah, so this is integrable still. So in the integrable case, of course, the spin transport is diffusive and the full counting statistics anomalous. I mean, anticipating the second question you could ask based on our paper from like a while ago, you'd say, well, what happens when you break integrability and maintain domain wall conservation? And there indeed, everything, you just have to replace t to the 1/2 with t to the 1/4 in every equation, and it just goes through. So this is not an integrability effect. It's like really a constraint effect.
Thanks, Sarang, again.
Thanks.